talk a little bit about machine learning. There we go. So at the top, you can see we have the big umbrella of machine learning. We've got the guy with all the neurons shooting out of his brain. That's kind of what you'll see if you Google artificial intelligence. And then under that, we've split things up into three categories. These are three different types of machine learning algorithms. Some of you might be familiar with some of them. From left to right, we have supervised learning, unsupervised learning, and reinforcement learning. And these categories are kind of separated by the type of input or the type of data that they use to learn. So on the far left, we have labeled data, then unlabeled data. We'll talk a little bit more about what that means in a second. And then we have a reward or a system of fitness for reinforcement learning. Today, we're really going to be focusing on supervised learning, which is the one on the far left. But I'd also just like to talk for a second about what each of the three of these are, or kind of what they include. So reinforcement learning, I always think of if you've seen those kind of clickbaity YouTube videos that are teaching an AI how to walk or win at chess or things like that. You can kind of think of it as something that can be used to win at game type systems. And then for unsupervised learning, we have clustering. Oh, yeah?
I think the slides aren't shared
on Zoom. All right, no worries. Yeah, the slides, we can email those out to you later, and there should also be a recording. Sorry, I just think I need to change some of the settings over here as well. All right. Okay, is that all good, Brian?
Yeah, that's good.
Yeah, thank you. So to continue, we were kind of talking about these different categories. I think we were on unsupervised learning. So a great example of that is clustering. Some of you might have done k-means clustering in some of the classes you've done. That's kind of one of the introductory types of clustering algorithms. And that's kind of trying to find underlying patterns that are inherent to the way that our data is distributed. On the other hand, supervised learning is going to be trying to find a relationship between our input and output variables, and then doing something with that, which kind of depends on whether we're using regression or classification. So I want to talk a little bit more about what we mean by labeled data and how we use it. So here we have a few tables. Each row on this table is an exam that I have or maybe I'm about to take. And then in the columns, we have variables like how long I studied, maybe where I studied, and then the grade on the exam. The one on the left is our labeled kind of training data, and you can see that we already have the grades for these exams. So the way that our algorithm works is we're going to pass it this labeled data. It's going to try to identify a relationship between our input variables, the hours studied and the location studied, with the grade. And then we can pass it our unlabeled data here that just says hours studied and location studied. And then we're going to try to identify our grade. I'm going to squeeze by this way. To kind of drive home the point of labeled data, I have a little demo that I'd like to do. Would anyone like to come up and be our supervised learning algorithm? Any volunteers? This does involve donuts. All right. Feel free to come right up and we'll get started. I'm going to kind of set up this end. Sweet. So right now, you're going to be our supervised learning algorithm. And as such, I'm going to need you to forget everything you know about the world, and more specifically donuts. And we're going to teach you how to identify, this glove is too small for me. I'm going to teach you how to identify some of these different types of donuts, okay? So first things first, this is a glazed donut. You know it's a glazed donut because it's round and it has glaze. Looks like he's got a good view. Next, we're going to bring out Boston cream donut. Boston cream donut is round, has chocolate, right? Following?
Following.
Good. And then this is our jelly-filled donut. We know it's a jelly-filled donut because it's round. You can kind of see there's some jelly in it. Sweet. You've been trained, all right?
All right.
So now we're going to test your training. Are you ready?
Yeah.
This right here, what is this?
That's a glazed donut because it has a hole in the middle.
I don't think I mentioned the hole in the middle. What type of factors did we learn about for the glazed donut?
It's round.
It's round. What's on it?
Glaze.
Glaze, that's true. What do we have here?
A Boston cream donut.
Yeah. And why is it a Boston cream donut?
It's round.
And
It's brown.
we'll take that. All right, I'm going to throw you a curveball. You ready? What do we have here?
Well, it's round and it's brown, so it must be a Boston cream donut.
Look at that. So I think an important thing we can kind of determine from this example is that our classification algorithms are going, or more generally our supervised learning algorithms, are going to be based on the type of data that we give it, and that's all that it's going to know. It's not going to be able to draw any connections beyond what's kind of represented in the set. Thank you so much. All right. So now that we have an idea of how supervised learning works, we can get back to these later. I'm going to go ahead and get more into the specifics about regression versus classification, right? So generally, we can kind of boil down the difference to the type of output that we have. So in regression, usually our output is going to be quantitative, like our test score for the previous example, predicting maybe a student's salary based on a few factors, or predicting the position of a falling object based on how long it's been in the air. I like that last example because I think it shows that regression isn't always the same as linear regression. Usually linear regression is the first thing we kind of learn about when we're going through these algorithms, but if you've taken any physics, you might know that the position of a falling object is a quadratic function. So regression can follow models that are different from just linear. We also have classification, which is when our output is categorical. So for example, determining what type of pastry, originally I was going to go to a bakery, but I just got donuts. So what type of pastry or what type of donut we have based on its shape, texture, topping, or predicting whether my favorite baseball team is going to win or lose their next game based on a few other factors. And then now I think to get more in depth into regression, I pass it over to Tiffany.
Okay, so let's talk about the simple linear regression. And linear regression is just a linear approach to modeling the linear association between a scalar response and the feature variables. And when we have just one feature variable, that's called simple linear regression. That's what we are going to talk about. And when we have more than one variables, that is multiple linear regression. And here is just a graph to show the simple linear regression. And usually we can use linear regression to make some prediction. Like if we know someone's weight, we can predict his height. And if we know individuals, like years of experience, we can use that information to predict the salary. And these blue dots are the data points we have, and the red line is the prediction rule we draw from the data set. And here, so how do we predict someone's salary based on just one feature variable, his years of experience? And now assume we already have the data set of like a number of individuals, years of experience, and his or her salaries accordingly. And we need to follow two steps. First, we need to choose a loss function. A loss function is used to measure the difference of our prediction and the actual observation to see the accuracy of our prediction rule of the linear regression. And usually we can see squared loss and the absolute loss, and they are in different formulas. And so next, we need to find the best prediction by minimizing the difference, the error between the prediction of the observation. And we call that empirical risk. And by definition, the empirical risk is just the average loss on the data set of our predictions. So in linear regression, we have two kinds of variables. So really, there are x and y. The x is feature variables, also called predictor variables, and they are used to describe our individuals for their attribute. And we use numerical variables to represent an individual's height, age, and in our case, it's the years of experience. And we also have categorical variables for the education level, for the college, and the Boolean one for if someone knows Python or not. So there are only two outcomes, 1, which means they know Python, and 0, which means they don't. So the second kind of quantity variable, which is why we used, also show in the graph we introduced before. And this is the quantity we're trying to predict based on the x, the feature variables. So in our example, y is a prediction of someone's salary, and x is the feature for his years of experience. Okay. So now, since we believe there's a linear relation for one individual's salary and his years of experience, we can say salary is an equation age of years of experience. Then it's a simple linear regression prediction rule. And age is called hypothesis function or prediction rule, as I mentioned many times. And our goal is find a good prediction rule. And how do you guys think we can find the good prediction rule? Like which kind of method we can utilize? Do you have any ideas? Okay. So we would just use the loss function. I mentioned it before. And I mentioned there is actually the squared loss, y minus prediction squared, and the absolute loss, the absolute value of the difference between prediction and observation. So which loss function do you think is better for the linear regression? Just a little hint, we need to minimize the error between the prediction and the observation. And the error is represented by a function. So, yes?
Would it be absolute loss?
Actually, not. The other one, the squared loss. Like, we know the squared loss is a quadratic function, and if the quadratic function is look like this, right? And if we take derivative and we can find the minimized point, we set to the derivative to 0 and find the minimized point. It's about calculus. And that's how we can minimize the empirical loss, because we want to find the smallest error of a prediction rule, and the prediction rule is just a function. Like it can be y equals x squared. So if we take derivative when x equals 0, the error is 0, but it's actually not realistic. And okay, so we will use the squared loss. And if we use the squared loss, our prediction rule, the error becomes r squared equals the sum of yi is the observation, like the real data of someone's salary, and the hxi is our prediction based on our prediction rule. And we squared that difference, we sum them, and takes average. That is the average loss. And we can use this function to quantify the quality of prediction when the r squared of h is minimized. That's the best fit prediction rule, right? Okay, now here comes a question. Suppose we have y1, y2 towards yn salaries. Which plot could be the r squared h? And r squared h is right here. It's a quadratic function. So which plot? Actually, you can guess. Don't worry.
A?
Yes, that's correct. Can you explain why?
Because the loss function must be non-negative, and there's like no way salaries will be negative, so the most of the functions should be on the first quadrant.
And what about the choice B?
It's not a quadratic
Yeah,
function.
correct. So choice B is the polynomial function, and we know the R square of h, our integral is a quadratic function. And what's your name?
Samuel?
Samuel, yes, Samuel explained correctly, because for D, the minimized point, our salary here, the y vertical axis is recording the arrow, but our arrow cannot be negative, and for the choice C, the salary cannot be negative. So the correct answer is B. Is A. So next, when we minimize mean square error, we know it's a linear relationship. So we can believe h of xi, our prediction rule equals w0 plus w1 xi, and w0 and w1 are our parameters to define the prediction rule, and then the mean square error becomes a function which takes in two parameters. And actually, it's not h here, it should be w0 and w1. And when we extend this function from here to here, we just expand the hi into w0 plus w1 xi. And we take the square, take the sum, and take average. So now we only need to compute the gradient, the derivative of r squared respect to w0 and wy, because it's a function about w0 and wy. We find the gradient and we set it to 0 to find the minimization situation. And here is the sum of calculus and expanding. And I think we don't have so much time, so we just look at the result. When we take the derivative of r squared to w0, we have yi as our observation minus our prediction represented by the hx, and take the sum divided by n and times -2. And here, respect to w1, we just times xi here. And we can solve for 0. The star on the top right of w0 means optimal, which means when we have w0 star, that is our optimal parameter to minimize our error of the prediction rule. And from the calculation here, let's just see the result. W0 equals y bar minus w1 x bar. And w1 actually shows the strength, the relationship of the feature variable, which is our years of experience and the salary of an individual. It shows the relationship of these two variables. That's W1. And W0 is the bias constant. And the result is y bar means the mean of variable y, and x bar means mean of variable x. So, and also some calculation. I think we will post the slides, so if you're interested in, you can just see the calculation after the workshop. And here we have W1 equals to blah blah. Here, yi minus y bar times xi, and take summation over the summation of xi minus x bar times xi. Yeah, it's all about calculation, and we are now only interested in the result. So it might be some complicated for the previous provement and the result. But let's see this question. Actually, it is very simple, and you can try to answer it. Like, consider a data set with just 2 points. We only have 2 points, not 3 points, so it's easy here. 2, 5, and 4, 15. Suppose we want to fit the linear prediction rule by minimizing mean square error, the best fit line of the data points, or value of W0 of W1 are optimal. Do you guys know the answer?
D.
What about yours?
Yeah, D.
Yeah, yes, that's correct. Can you explain?
Because if we fit the 2 points into a line, and the slope will be 5, so W1 should be 5, and then put 2, 5 into the slope of the line, and we'll get that W0 should be -5 in order to fit the 2 points in.
Yes, yeah. So the gradient is we use 15 minus 5 divided by 4 minus 2. That is 5. And we know y equals W0 plus 5, which is W1 times x. And we just plug in one of the 2 points, we can find W0. So the correlation coefficient, actually, I think you guys know the correlation coefficient is just a measurement to show the strength of linear relationship of 2 variables, and it's calculated by standard units. And standard units is xi minus x bar time divided by the standard deviation of x. So it's a way to standardize a variable quantity. And according to the definition, the average of the product of x and y, we can know the correlation coefficient R equals here to product of xy's standard unit and take summation divided by n. And W1 now can become R times standard deviation of y divided by standard deviation of x. And it is an easier way if we know the standard deviation of the 2 variables and we calculate the correlation coefficient, it's more easier to calculate the result. And here is an example of how we usually utilize these formulas. We have 3 points here. We don't need to calculate. We have 3 points here, and we can calculate the mean of x variable and the mean of y variable. And using these formulas, we can get the answer of W1 star and W0 star. It's just some simple calculation. And it's a simple example. When we have more than one feature variables, for example, we just predict one's salary based on experience throughout the slides. But actually, in real life, it should depend on more variables like years of education, the location of the individual live in, and maybe the education level of that individual's parents. And at that time, that's called multiple linear regression, and the feature variable x become vectors, like the vectors in Rn. Do you guys know the linear algebra? Yeah, cool. So then that's more complicated if we use linear algebra, but we only have a simple linear regression here. Okay, here comes the.
All right. Unfortunately, our live recording of the workshop did cut out around the time we were getting finished with regression. So I'm going to be going through the slides for the classification problem here for those of you who might be watching the recording from home. So the classification problem on paper, as you can read right here, is pretty similar to the regression problem in the sense that we're still using labeled data and it's a supervised learning algorithm, but this time we're trying to assign a category to each observation as opposed to a quantitative value. Another thing that makes classification a little different from regression is there's many different ways we can go about solving this problem. With regression, it's sort of the case that regardless of whether you're doing linear regression in 2 dimensions, or quadratic regression in 5 dimensions, or sinusoidal regression in 200 dimensions, once you kind of learn about the linear algebra that goes into regression, your approach to solving it is going to be pretty much the same each time. However, as you can see, we've got a lot of very different methods to solve the classification problem. On the left, we've got the naive Bayes classifier. That's what we're going to be talking about today, and it's also probably the first type of classification algorithm you'll learn about if you're going through the data science curriculum here at UCSD. And that classifier is mostly based in kind of mathematical probability and this theorem called Bayes' theorem that we're going to learn about in just a second. In the middle, we've got decision trees and random forest. Those use the tree data structure that you're probably familiar with if you've taken any data structures and algorithms courses. And then on the far right, you can see that we can even use regression as a method to solve our classification problems. But like I mentioned, for today, we're going to be talking about the naive Bayes classifier, and therefore we're going to be talking about Bayes' theorem. So this is a theorem that operates on conditional probabilities. If you're not familiar with those, it's kind of the probability that a certain event happens given that another event has already happened. And one thing that's true about those probabilities, or more accurately, one thing that's false about them, is that the probability of A given B isn't going to be the same as the probability of B given A. An example you can kind of use to understand the reason this is the case is you can assign event A to be the probability that somebody is a male, and event B to be the probability that they are a billionaire. So the probability of A given B is the probability that somebody is a male given that they're a billionaire. I think there's some statistic that like 60 or 70% of all billionaires are male. So you can see that's kind of a relatively high probability. But if we take it the other way around and try to calculate the probability of B given A, that would be the probability that somebody is a billionaire given that they're a male. And I'm sure most of us don't know a lot of billionaires, so that probability is going to be very small. And we can see that the probability of A given B is not equal to the probability of B given A. And Bayes' theorem is what we're going to use to solve this, to find the probability of one conditional from its converse. So I have another little example that we can kind of work through. The probability that I take the bus to school is 0.4. The probability that I'm late to class is 0.5. If I'm late to class, the probability that I've taken the bus is 0.65. And we want to know the probability that I'll be late to school if I take the bus. We can assign our probabilities to these events as such, set up what our Bayes' theorem is going to look like. Then we can substitute in the appropriate values. And finally, we can calculate that conditional probability, the probability that we're late given that we've taken the bus. So now you might be wondering, okay, this is great. We have this cool theorem that we can use to figure out these conditional probabilities, but how does this relate to the classification problem? Well, we're going to use this theorem in order to implement our naive Bayes classifier. So just to remember the problem, given an observation with a certain set of features, we want to determine which category it'll belong to. We're going to use our training data then to calculate the probability that an observation belongs to a certain category given its features, and we're going to do that for each category. So if we think all the way back to the donut example that I believe was on the recording, our categories would be glazed donut, Boston cream donut, and jelly-filled donut. So we'd calculate 3 probabilities: the probability that it's a glazed donut, the probability that it's a Boston cream donut, and the probability that it's a jelly-filled donut, given whatever set of features we're trying to kind of examine in that case. Then once we've calculated all those probabilities, we're going to take the one that is the highest probability, and we can just simply assign that category to that observation, because we've determined that that category is the one that is most likely to be true. So I do have an example we're going to work through to kind of see how our naive Bayes classifier works. Here I have kind of an extended version of our previous example, where for each observation we can see whether or not we took the bus, whether or not we hit snooze on our alarm in the morning, and how much sleep we got. And then we'll also see whether or not we're late to class. So here we want to calculate two probabilities, right, for our observation. We want to calculate the probability that we're late to class, given that you can see here bolded, we've taken the bus, haven't hit snooze, and only got a little sleep. And then we want to calculate the probability that we're on time, given that we took the bus, didn't hit snooze, and only got a little sleep. So let's kind of go through the different probabilities that we're going to need in order to calculate this conditional, and we can just kind of observe them from the table. So for instance, we're going to need the probability that we're late and the probability that we're on time. You can see there are 12 observations. On 6 of them I'm late, so we can just count those, and on 6 of them we're on time, so we can count those, and then each probability is 6 out of 12 and just 1/2. We also need to know our conditional probability, first for being late. The probability that we took the bus, pressed snooze on our alarm, and got a little bit of sleep, given that we were late to class. However, we realize that we have a problem. We haven't had any observations where these three features are true. If you look through the table, you'll never find an instance where we took the bus, pressed snooze on our alarm, and only got a little sleep. Our solution is going to be to calculate an estimate of this probability, or an approximation of it, using the product of our conditional probabilities. So instead of looking for observations where all three of those things are true, we're going to look separately for each observation, find the individual conditional probabilities, so the probability that I took the bus given I was late, the probability that I pressed snooze given that I was late, the probability that I got a little bit of sleep given that I was late. We're going to count those, and then we're going to multiply them to approximate the conditional probability for all three. So out of the 6 times I was late, you can see I took the bus on 3 of them, I pressed snooze on 4 of them, and I was a little late, I got a little bit of sleep on 3 of them. We can then multiply all those probabilities and estimate our final conditional probability as just being 1/6, which is the product of those 3. Now that we have that, the next thing we need to do is just calculate the same thing for when we're on time. So you can pause and look at the table if you want to, but it's just the same approach where we look at only the observations where we were on time, and then we count our values for each taking the bus, pressing snooze on our alarm, and getting a little bit of sleep. Now let's go back to what we want to compare. We want to compare 2 terms, right? And this is what they look like. This is the conditional probability that we're late, given that we took the bus, pressed snooze on our alarm, and got a little sleep on the left, and then the conditional probability that we're on time, given that we took the bus, pressed snooze on our alarm, and got a little bit of sleep on the right. What we notice about these 2 terms is that they have the same denominator. What this means is that if there's an inequality symbol in the middle, we can just multiply both sides by that probability, and then we realize that we only really need to compare the numerators. Therefore, we don't actually have to calculate the probability that we took the bus, pressed snooze, and got a little bit of sleep. Now that we know that we just have to compare those 2 products, we can go ahead and compute them, as we've already found each of those values. So we have all the probabilities that we need written up there. We're going to multiply the probability that we're late to the conditional probability of our features given that we're late, do the same thing for when we're on time, and then we'll see that our conditional probabilities are 1 in 12 for being late and 1 in 216 for being on time. We know that 1 in 12 is greater than 1 in 216. Therefore, the probability that we're late is greater than the probability that we're on time, and we're going to classify that observation as late. So that's going to wrap up our discussion of the naive Bayes classifier and regression and classification. If you're interested in learning more about these algorithms, we recently hosted a more practical application-based workshop that'll be uploaded on the same channel shortly, so definitely check that out. And we're going to have a whole series of upcoming workshops on machine learning, as well as some of the more mathematical data science topics, if that's what you're more interested in as well. We've got this QR code for feedback. It might be a little late by the time you're watching this, but we always appreciate it. But yeah, thank you for watching.